All right, let's pull back the curtain on maybe the most important piece of software you use every single day, but probably never think about: the operating system. It's this silent, invisible architect that makes everything on your computer actually possible.
I mean, just think about it for a second. How is it possible that you can have a dozen browser tabs open, music streaming, and a file downloading all at once, and your computer doesn't just melt? How does it all work so smoothly without just descending into complete and utter chaos?
Well, the answer is this master juggler working tirelessly behind the scenes, and that's the operating system, or what we usually just call the OS. It's the boss, the fundamental software that manages all the hardware and every other program on your machine.
Here's a cool way to picture it. Think of your computer as a bustling city. Every app you open, your web browser, Spotify, a game, is a citizen living in that city. And just like real citizens, they all need things. They need space to live, which is your computer's memory, and they need time to get work done, which is processor time. The OS? It's the city planner, the traffic cop, and the mayor all rolled into one.
Now, like in any busy city, things can get messy. People bump into each other. So what happens when two of our digital citizens, two different programs, try to grab the very same thing at the exact same time?
You get chaos, pure digital chaos. Imagine two programs trying to write to the same file at the same instant. The final result could be a garbled mess, or one program might just completely wipe out the other's work. It's totally unpredictable, and in the world of computing, unpredictable is basically a four-letter word.
You know, this exact scenario actually has a name. It's called a race condition. It's literally a race to see which program gets to write its data last, and whoever wins determines the final outcome. And that outcome is left completely up to random chance, which is pretty much the last thing you want happening with your important data.
So, how does our city planner, the OS, prevent this free-for-all? Well, it doesn't just let the programs run wild. It sets up traffic lights and rules of the road. This whole system of coordination and rule enforcement has a name: synchronization.
And the single most important rule at the heart of synchronization is something called mutual exclusion. It sounds complicated, but it's a really simple idea. One at a time, please. When a program needs to use a shared resource, it steps into a special zone called a critical section. And while it's in there, nobody else is allowed in. Every other program has to wait in line. This simple rule is what stops race conditions dead in their tracks and keeps all of your data safe and consistent.
Okay, so rules are good, but what happens when the rules themselves create a new, even weirder problem? What if waiting in line leads to a total, complete gridlock in our digital city?
This brings us to a really fascinating problem called a deadlock. It's a classic standoff. Picture this. Program A has control of the printer, but it's waiting for a file. And at the same time, Program B has the file, but it's waiting for the printer. See the problem? Neither one can move forward. They're stuck, waiting for each other forever.
Exactly. It's this bizarre digital version of after you, no I insist, after you, that never ends. The result for you is that the applications just freeze. Nothing happens. The whole system is gridlocked.
So to fix this, the OS architect has to step in and break the jam. And it can't be gentle about it. It might have to just kill one of the programs. Poof, it's gone. Or it might be able to roll one of them back in time to a state before it grabbed the resource. Or, and this is pretty bold, it can just forcibly snatch a resource away from one program and hand it over to the other. These are drastic measures, for sure, but they're necessary to get the city moving again.
All right, so we've talked about how the OS manages what all these programs do, but what about where they live? And that brings us to the next massive job for our architect: memory management.
So here's the basic conflict. Every program you run is kinda selfish. It believes it should have one giant, continuous, private chunk of memory all to itself, like a sprawling mansion on a hill. But the OS knows the reality. Physical memory, your RAM, is more like a city full of small, scattered apartments that have to be shared by everyone.
The OS's solution to this is absolutely brilliant. It takes the program's massive mansion and, instead of trying to find a place for it, it just chops it up into small, perfectly equal-sized pieces. These little chunks are called pages.
Then, it does the exact same thing to the physical RAM, dividing it into identically sized slots. And these slots are called frames. Now here's the genius part. Because every page is the exact same size as every frame, the OS can slot any page into any available frame. It's like a universal system of Lego blocks. It doesn't need a huge empty space anymore.
But okay, if a program's pieces are now scattered all over the place, how in the world does the OS keep track of everything? Well, it keeps a map. It's called a page table. You can think of it just like the directory in the lobby of a huge apartment building. It tells the OS exactly which apartment, which frame, each little piece of the program is currently living in.
This whole system of pages and frames is incredibly clever, but what happens when you want to run a program that's bigger than all the RAM you have? What if the mansion is bigger than the entire city?
And this is where the OS stops being just an architect and becomes a full-blown magician. It performs its greatest trick, virtual memory. It creates the illusion that your computer has a nearly infinite amount of memory. And the secret to the trick? It uses a piece of your much bigger but slower hard drive as a sort of magical overflow parking lot for your RAM.
So here's how the magic works. Your program asks for a page of its data that isn't currently sitting in RAM. Bam! That triggers something called a page fault. The OS instantly hits pause on the program, finds a page in RAM that hasn't been used in a while, shuffles it over to the hard disk for safekeeping, and then pulls the page the program actually needs from the hard disk into that now empty slot. Then it hits play. The program continues on, completely clueless that this lightning-fast swap ever even happened.
Now this raises a super important question. When the OS needs to make room, which page does it decide to kick out? The strategy it uses has a huge impact on your computer's speed. It could do something simple, like first in, first out, where it just boots the oldest page. But a much smarter way is called LRU, or least recently used. It looks for the page that's been collecting the most dust and swaps that one out, betting it won't be needed again anytime soon.
So, when you put all of this together, managing conflicts, preventing system-wide traffic jams, creating illusions of infinite space, you start to really see the genius of the operating system.
It truly is the invisible architect. Its entire job is to solve these incredibly complex, mind-bending problems so that you don't have to. All of that tireless, brilliant work is happening in the background, every millisecond, just so you can click, type, and have everything just work. And this is why all of this matters, because a digital city is getting bigger and way more complicated. We're moving to massive global clouds, we're on the verge of quantum computing. These new frontiers are going to need new rules, new kinds of architecture, and frankly, entirely new kinds of magic. So it makes you wonder, what do you think the next great illusion in computing is going to be?